Let's see, do we want to take a look maybe at some questions from the assignment?
Number 6.
Number 6. Okay.
Frequently asked questions.
Frequently asked questions.
Shook muscles.
How do I do that? Oh. Yes. Hang on 1 second. Hey, can I have your attention up here, please? I want you to put your conversations away. I want you to focus up here. We're getting a little bit of a late start. So, what was the question? I'm sorry.
Number 6.
But someone else had a question. I said just a second.
Oh, do we need to have our workshop for that statement since it's like all graphs?
Not so much for that one. Yeah. Okay. Here. This is the assignment, right?
Yeah.
Remember you guys did. So number 6 is the one there were questions on. Mainly, we'll start with that one at least. This guy. Yeah, this is a good one. Real good one. Good one to talk about. Okay, so that's really small, isn't it? Let me.
It doesn't really get bigger. Can you?
Yeah.
Can you like skip that and then I go into like?
Yeah, I'll get it worked out here. Okay. And I'll make these bigger. There we go. Okay, so
I took better small.
Yeah, they're easier to see the dots.
easier to see the dots when it's smaller?
Yeah.
Really? Oh, for you guys it's easier? I'll make them bigger. Okay. I'm going to pick the right one for now, and we'll talk about why that's the case. Would everybody agree that all of these, you looked at this one, right?
Yeah.
All of these graphs are structurally the same. The only thing that's changing is the species of endpoint, and right, does that make sense? Are they open or closed? Okay. So this is the right answer, and let's talk about why that's the case. Let me copy this. Okay, move out of the way. You see that?
Yes.
Okay. All right. So that's closed, 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 and the rest are open. Okay. Now, why is this? They want a couple things here. First of all, they want you to pick the correct graph. This is it. Okay. Why? Well, here's our piecewise function. The function is broken into 3 parts. You know, we could talk about why the square root of 36, which is just 6 squared minus x squared, looks like this. It's really just a circle centered on the origin, isn't it? Or the top of a circle, right? Because it's a function. So it's the upper half of a circle centered on the origin. But the graphs are all the same. So I'm not even really concerned that you knew that. You knew that that was the curvy part of the graph, though, right? Okay, so this is the curvy part. This is the horizontal line at 6. That's a 12, and that's a 6 right there that I blocked off. And then finally, we've got when x equals 12, at that one point, the value of the function is 12. So that's a point, correct? Okay. So why is this the correct one then? Well, look at the behavior of the domain, right? Look at the domain here. The curvy part of the function, which we're going to color code blue, is the one that is defined when x is greater than or equal to 0. Now, what's that mean?
It's an open, no, it's closed.
Closed, right? Because, now let's talk about that, because it's filling in the endpoint, right?
Yeah.
So just, I'm sure you know this, but let's just make sure, if I'm like graphing the line segment, let's say that's going from 1 to 4, if I graph it like this, that is not including the endpoint because it takes less ink, right? You know this. And then that is including the endpoint, right? Okay. So given that, then we know that this one has to have a closed endpoint on the left. X is greater than or equal to 0 and less than 6. What's just the less than 6 mean? Open endpoint, because it's not including 6. It's just everything up to but not including 6. So we got to have an open endpoint. So this is it right here. Whoops, wrong color. So this is it right here. Closed endpoint, that's our curvy part of the graph. Open endpoint. Okay, check. Yes, ma'am.
Why does it start at 6?
Why does it start at, well, because that's the shape of the curve. If we were to graph that, this is just saying the square root of 36 minus x squared. If I were to graph that function, it just looks like this. It goes out, it's got a radius of 6, and it's just a hemisphere like that.
Yeah.
Okay. Right, if you graph that on your calculator, that's what you'd see. Okay, so we're just taking that graph, but only taking the part of that graph that's going from values greater than or equal to 0 and less than 6. Okay? Questions? Okay, good. So now let's move on to, how about the green part of the graph? Now we've got the line f of x or y equals 6. Well, what's that? Straight horizontal line. Look at the domain here. The domain for this one is x is greater than or equal to 6, so closed circle, good, and less than 12, open circle. Okay, so this one's going to look like that. Okay, questions? Okay. The last part, the red part, y equals 12, would be a horizontal line, and it is. The graph's a horizontal line, but it's only graphed when x equals 12. So it's just one point from that horizontal line, one way to think about it, right? So that's going to be the point right there. So that works, doesn't it? Okay, the endpoints work the way they're supposed to. But if we looked at any of the other possibilities, it would have been messed up. Maybe that would have been open and that would have been closed, and that, you know, I mean, they would have been different and incorrect. Okay? Okay, now the rest of these are really good questions. What are the domain and the range of f? Well, first of all, I think there was some question, probably based on the fact that it's just the end of the summer here, about what domain and range are. Somebody articulate for the group, please, what a domain is. Yes, right.
Domain is x and range is y.
Okay, good. The domain is the set of all values of the independent or input variable, right? So all the values that are available for this function reside in the set called the domain. Now, a lot of times the domain, if the domain is not stated, and let me just be clear about this and maybe even take just a second and review. Okay, if the domain is not clearly stated, if no restrictions are put on it, like for example, what if we have the function f of x equals x squared? What's the domain? What are all the values that x could have? No limit, right? It'd be all real numbers. Okay. How do we write that? Okay, so good. So we could do it this way. We could say if it's all reals, we could just say, okay, what in the world does that mean? Is that a point?
No. Everything.
Good, that's interval notation, which is the other thing I think maybe we need to spend just a second talking about today. I got a lot of questions on that, and I want to make sure everybody's clear. It's just a notational thing. But in math, a lot of times we'll have different types of notations that serve different purposes. Traditionally, when we're talking about domains, we would either use interval notation, which I think is preferable, or we could use inequality notation. And maybe we'll look at a couple examples. Which question was that? Wasn't there a couple of them maybe, right, that asked you to do some, maybe this was one of them actually, wasn't it? Okay, on this, yes, this will be the one, that'll come up here in a second. What does this say then? When we're talking about interval notation, if I want to say something like this domain in interval notation, x is greater than or equal to 1 and less than 3, how do I say that?
Like, when you're drawing.
You would do like
Using interval notation.
a bracket, 1, comma, 3, parentheses.
Okay, good. So that's going to look like a bracket on the left because it's including that endpoint, right? Here's a way to remember that. A bracket takes a little bit more ink to draw than rounded parentheses because it's including the endpoint, okay? So we'd have a bracket, bracketing the 1, saying that the left edge of the domain is pushed all the way up to and including 1. The right edge of this part of the domain stops at 3 but not inclusive. Okay, does that make sense?
It's just less than.
Just less than,
That means
yeah.
it's a parentheses.
Yep. What if we add something else to this? What if we say, or, and we can do that with, I can't remember what you can call that thing. The U thingy. Or x is greater than 5, let's say. How would we do that?
You.
Okay, we got a couple options. We could do this symbol. Whoops, supposed to be blue. We could do that symbol and then go, get out of there. 5, infinity, right? Or we could do this, comma, that's fine. Commas are acceptable. They separate parts of a domain.
Wait, why wouldn't infinity have a bracket?
Because it
You're
goes
right.
on.
Okay, because you can't, because it's not a number, right? Okay. What if we added to that one more part? Let's say we also add to that. I'm going to add in here. What if we also stuck in there an or x equals 4?
Instead of the bracket.
Okay, so there's a bunch of ways I could do this. So if we're going to add this part now, we could write it like we've got our 1 to 3, comma. We could say, well, that's not going to work, is it?
You do the like a table bracket.
Yeah, good.
The,
So,
yeah.
right, so we could do, if we have to do a discrete point, we do this.
Oh, gee.
I can never draw those.
Okay.
How do you draw that?
How do you find them on the computer?
They're on the same button as brackets.
Oh, how do I draw? I'm just really talented.
Like you're doing.
Yeah, no, it's not hard.
Like all teachers
Okay,
should be like that.
make sense?
Yeah, yeah.
Okay, if we wanted to include, question?
I was just gonna ask, it doesn't matter what order they're in.
I don't know the answer to that, but to me it does. I would always want to do it so it flows from least to greatest, so it looks like a number line. And I really want you to do that because I'm going to show you kind of a trick later on in the year. There's a way that I like to teach optimization stuff, and it uses that same concept. So we always want to go least to greatest, just like a number line. Okay. What if we had a couple different points? Like what if x could be 4 or x could equal 4.5?
And you do the same thing.
Good, good. Okay, so yeah, we could just, in that case, we would just do this.
Oh.
Does that mean it's spanning that distance? No, it means it includes only those discrete values. So this is set notation, and it's consistent in math. Set notation means it's like a list. In programming, we call it a list. It's a set of these discrete values, okay? All right, so, does that make sense? Yes?
I don't know if like this would ever happen, but if you had like one more, like or x equals 4.7, would you put another? Would
Yep.
you have to like do completely different stuff?
No, you just put it right in this
Okay,
list if you want.
could have like
Yeah.
3 of them. Like,
Yep. You could separate them, but you don't need to. Yeah. Okay, good question. All right, so I gotta go. Where was I? Back there. There we go. Okay. So, the domain and the range then. What's the domain of this function? What are all the values of x where the function is defined? Now, you gotta be careful with this. I can see why at first it's really hard to, once you create the neural network that houses all this information, it gets very simple to recall it and use it. But initially, there's a lot of competing concepts going on here. Think about it, because I mean, limits are so fundamentally different. You're gonna look back later and say, wow, it's not that big a deal. But at first, it's a little bit tricky. It trips you up. When we're talking about a domain of a function, we are talking about the actual values of the function. Limits aren't really an issue here at all. We just want to know in ant language, if an ant walks from the left edge to the right edge, where can he stand on something? Right? Where is the function defined for him to stand on? What do you think, Julia?
Bracket 0, 12.
Good. Okay, right, good. So part A, the answer to part A, and let's talk about why that's the case. So A. Okay, somebody else, why? Why is that the case? What do you think? Yes, ma'am.
Because from 0 to 12 on the x-axis, there's a point. On the function, there's a point.
Okay, there's always a place for him to stand, right? Is it a problem? What's going to happen here is the ant walks along this function. When he steps there, he just beams up to there, right? Is it a problem that he's jumping vertically? No.
If it's one dimensional, then would you just like look at x and then like wouldn't even be beat up?
Right, exactly. If you were looking from above at the ant walking, you would just see him walk along unobstructed the whole way, right?
Yeah.
Okay? That's the vantage point that really we would take to answer that question in a way. It's a good way to think about it. Question? No, question? Cheyenne, do you have a question about that?
No, I
Okay.
think I answered.
Right, so don't confuse this with the limit part. That's coming, right? The domain is just where is the function defined? Every place on that interval. Okay, questions? Good, so far? Okay. B, at what points C, if any, does the limit of f of x as x approaches C? That's how we say that, right?
Maybe we have to put a range.
Yeah.
Range, whoops, yeah, skipped. The range. Okay, the range of the values of y. The values of y are, I think, a lot harder to find mathematically, but graphically it's no harder. Okay, so graphically, if we're trying to find the range, the values of y for which the function produces, let me say that a different way. What is the set of all output values of the function? This time I would kind of look from over here, wouldn't I? I'd be looking horizontally at the, back perpendicularly at the y-axis. And maybe I'm looking at the shadow of all these functions on the y-axis. Where would I see that shadow? Okay, does it exist at y equals 0?
No.
No, it doesn't, does it? Because that's an open circle. So the function does not exist there, so that shadow is not going to start until you pass beyond 0. Make sense? Okay, so for the range, it's going to go from 0, right? Start all values where y is greater than 0. Okay, looking from the side, it's going to be fine until I get up to what? 6. And at 6, does it exist? Are there y values?
Yes.
Yes. Okay, so comma,
And then the
Why?
with
comma.
the
Okay, good. Then the only other place is going to be at 12. When I look horizontally at this, I see a big gap where there are no output values, and then there's a single output value at 12.
Why couldn't the ant jump up to 12 like it did before? Okay, I got it. Yes.
Okay, because this is counterintuitive. We're looking at the y values now.
Okay.
Okay, make sense?
But because that R
because there's nothing
6.
Mhm.
Why is it start at 0 though?
Because-
backwards.
Well, it doesn't. Okay, it doesn't matter. it doesn't matter where he starts and where he ends. We're just saying if the ant, I don't want to do this. If the ant is, okay, here's how we're doing this. This is contrived, but bear with me. So pretend we put a piece of photographic paper on this axis and we're shining a light from up here, right? So that means that as the light's shining, the ant is going to block out some light as he walks, and it's going to make an imprint on the photographic paper, right? Where is there going to be some shadow left on the photographic paper? We don't care when he gets there, right? But as he's walking down this part right here, isn't he shading, right? There's going to be some shadow cast from there down to there, right? Agreed? Okay. Then he jumps up to here, but that's okay. It's already in shadow. He walks out this. It's still just, that's already been in shadow. He's not changing anything, right? But when he gets to here, he jumps up to this spot, and we cast one little point-like shadow right there, right? So the shadow on the y-axis is just going to be there and that part, right?
Oh.
Okay, make sense? Okay. Okay, so questions on that? Okay. What about part B? At what point C, if any, does the limit of f of x as x approaches c fail to exist? So may I erase this? Are we okay with that?
Yeah.
And I'm recording this, so it'll be available. Okay, so okay. Yes, sir.
Are we ever gonna have like points that are in different quadrants?
Sure. Yeah, we could. Yeah, we could. This because those are all in quadrant 1. No, they wouldn't have to be. They could be anywhere. Okay, so now I really want you to be. There's a part at the end of section 1.2 called the rigorous definition of a limit or something like that. We're going to come back to that. It's really you'll be better prepared to deal with it later. It's kind of a very dry, abstract, mathematical, formal definition of a limit. I want you to see it, but I don't want it to interrupt our momentum because it's you're just going to go, what? I mean, it's weird, and it's not super important, honestly. But I do want you to have a really good feel for what this limit means. How do we say that, first of all? Everybody in unison. We'd say this as the limit of as x approaches c is whatever. Yeah, whatever. Usually we'd say it's an L. But in this case, what we want to know is, does it exist? Think what this means. We want to know the limit of the function means what is the y value approach as x approaches c. Okay, here's where you got to completely change your thinking, right? With a limit has nothing to do with the value of the function at c, right? They're completely disconnected because in the limit, you never get there, just like I never get to the door, right? The limit is exclusively dealing with what is the limiting behavior. What is going to happen as I get infinitely close to that? What do I anticipate is going to happen? What does the behavior of the function cause us to think is going to happen when we get there, right? Okay, for the limit to actually work then, to exist, we have to agree from both directions that we're going to land on the same point, okay? If that doesn't happen, the limit doesn't make sense because the function doesn't behave in a way where it predicts a single value, okay? Does that make sense?
Yeah.
Right? Okay, so then at what points does I can't believe they asked about I'll tell you what, I didn't see this was on here.
Those were.
Yeah.
There's no question. It doesn't
Ignore that one. That one we'll get to later. Okay, that's not for now.
Well, it asks you, but it never actually asks you a question. It asks you there, but it's never.
Oh, okay, I remember I took this off year before, but I think I just forgot to erase it there. Yeah, so ignore that one. That's for next week. At what point, C, if any, does the limit exist? Okay, so let's walk along this graph and find all those places. Okay, here's our trip. There's our ant, starting right there. Does it, okay, first of all, does it exist at that point?
No.
Okay, now this is a really tricky one. Think about our definition of a limit though. The limit has to be the place where ants walking from either direction would agree
There's no.
on, see ya, would agree on where they're gonna step, right? What's the problem with that statement here? There's no other direction, yeah. See, we can't apply that definition because the ant has nowhere to stand to the left of that point. Make sense?
Yeah.
So technically, the limit does not exist at that end point because you can't approach it from both directions. Now, as you might guess, based on this question, we're gonna talk about some mechanisms where maybe we can save the day there and say, okay, a regular limit, which we're gonna come to call a two-sided limit, doesn't exist, but what about a one-sided limit? What if we only said you had to approach from one side? Well, then it would be okay, wouldn't it, right? But for now, we're not there yet, so with a regular definition of a limit, the ants have to approach from both sides and agree, and they can't agree there, so it doesn't start there, does it? Right? So the limit doesn't exist at 0, but as soon as I start to move to the left at all, then an ant can approach from that direction, right? And it does exist. Make sense? Okay, does the limit exist? And this is a very important question. Does the limit exist right there?
Yes,
Okay, it does. Why?
because both sides can move.
Okay, good. Now, we tend to focus on the weird points. Like, when we get down to here, we're going to have to discuss that a little bit. And we ignore the regular points in the middle. But limits exist whether or not the function exists there. In most cases, the function does exist there, and the limit doesn't really do anything that special, right? So, yeah, it does exist there. It's because the ants think they're going to land where they land, right? Or they both think they're going to land at the same place. Doesn't matter where they actually land. Okay, but keep walking down here, but then what happens when we get to x equals 6? Okay, I heard the limit doesn't exist. Why?
Because it goes up to 6.
Because it goes up to 6. So how would we describe talk to me about that. Okay, so there's a break in the function. I think the textbook says functions where the behavior differs from both sides or something like that, but it's really, most people would just call it a break in the function, okay? There's a break in the function. The problem being that the ants from the left are going to think they're going to step on y equals 0. The ants from the right believe they're going to step on y equals 6. Does it matter who's right?
No.
Makes no difference. They don't agree. They never get there anyway, but there can't be a limit because they disagree, okay? So there's our first place where the limit doesn't exist internally. And then as we walk along the function, continue towards this point right here, does it matter that that point is up there? Makes no difference, right? Either way, we don't have a limit there because it's an endpoint. Okay? Make sense? Right? Okay, so then, how would we answer B? So, all values of x greater than 0 and less than 6, or values of x greater than 6 and less than 12. Yes, ma'am.
So the places where the open circles are, that's where the limit doesn't exist.
Right.
But everywhere else it does.
Everywhere else it does. Right.
But that's a solid point, so why wouldn't it be
At where? You mean at 0?
Yeah.
Okay, because remember that's an endpoint.
Oh, okay.
That was why. Okay, now there's something else.
What about the 6 on the starting, where it starts at?
Oh, right here?
12?
Oh, I got you. Why isn't that solid? Because
Oh,
that's a break in the function there.
Oh.
Right? Because remember, we don't actually get to 6. As we approach 6, ants would think they're going to land on different spots, and therefore, because there's 2 answers, we can't have a limit.
So would we never have a bracket when we're talking about limits then?
No, you could. You could. Okay. No, at this point we can't. That's a good question. You're right. Until we get one-sided limits, you couldn't. You're correct.
Wait, why did you split them up? Why can't it be just 0 to 12?
Say it again.
Because
Why
it's
did
breaks
you
in the
split
function.
0 to 6 and then 6 to 12? Why isn't it just 0 to 12?
Because right here, we've got a break in the function,
Okay.
right? And so the limit, where are the 3 places again where limits don't exist?
Break.
Okay, breaks in the function, and why is that? Because the ants anticipate different spots. Ants from the left and ants, that's backwards from me, ants from the left and ants from the right would think they're gonna step on different spots. They disagree, so no limit, okay? What's another kind?
The sign.
Oh, okay, we got the last. What's the middle one?
Asymptote.
Asymptotes. Either infinite up asymptotes, infinite down asymptotes, or split asymptotes would be pretty obvious. How come, let's take for example an infinite up asymptote, where it looks like an infinite peak. Why is that not a limit? It's infinitely climbs, okay? So can the ants ever agree on a single place where they're gonna? No, every step they take closer to the asymptote shoots them up more rapidly, right? Agreed? So that's also a no limit situation. And the third one was the wacky one with the oscillating behavior. And that's a weird one. Questions on that? Does that make sense? Okay. Last one. Oh, that one's gone too, right?
Yeah.
Okay, good. Okay, now I have one question for you though. Why do you see a problem with, and we got to get to the bottom of this. This was fine over here, wasn't it? Because we said, okay, we can't have the endpoint at 0 be, the limit doesn't exist there because you can't approach that one point from the left, right?
Yep.
But an ant could stand on 0 and start walking to the right along the function. So every point beyond 0, at least up until 6, was fair game. Agreed?
Yeah.
Okay. Now it's a different situation on the right though, isn't it? And this is kind of cool. I want you to think about this. In this case, we have to exclude 12 because it's an endpoint, but if an ant stands on the function at 12, he's standing up there. And if he takes a step to the left now, he's going to have to plummet down to the adjacent point, right? And so then, isn't that next point going to also have to be excluded because it becomes the endpoint? You see what I'm saying? Do you get the problem? Okay, turns out it's not a problem, but I want you to tell me why. Doesn't that seem a little perplexing? Okay, it's important conceptually to make sure we understand why that doesn't matter though.
Because the line goes, like the pathway the ants step on goes all the way up to 12, but not including it. So
Right.
it's like as soon as they step off of 12, they'll just be, even if the 15's.
Okay, I know you understand that. See if we can articulate that a little differently. See the problem, you understand, once again, the problem is, this one, we said over here, it's no problem because 0, x equals 0 is the endpoint, but if an ant stands on that one point, no matter how small his steps, he's always walking to the left, and so the next point's okay. Okay? Here, he's not standing on the connected point, right? When he steps from x equals 12 backwards, he's going to land down here at the adjacent point. Does that concept really have any meaning though? Adjacent point?
Like he
Because
will
it's still
always.
next to that other.
He's going to go to the left, but as the ant steps to the left, he's going to step off of that step down to here, right?
Yeah.
And he's going to land on a point.
Yeah.
And the suggestion I was making, which is nonsensical, but I want you to really articulate why this is nonsensical. Doesn't that cause a problem? Because doesn't the next point to the left then become an end point and therefore a place where there's no limit?
No, because this is the one that knows what you're approaching.
You're right, it is.
Because then
It
you
is.
get to that
But is there such a thing as the next point?
No.
Ah, that's the weird concept. You see that? You see how if there were a discrete number of points on this line, we would have to do something else here and say, oh, it's not really 12. It's like 1 point over from 12 is where we'd have to stop because that becomes the end point, right? Because that 12 is there. As soon as we move to the left, we're down here again, and we got a new end point. But there is no end point there. That's the point I'm making. Maybe this is, do you kind of see how that's a little strange? But it's true. There is no such thing as a next point. If you think you step to the adjacent point, how many points did you actually step over?
like,
An infinite number.
There's an
Right.
infinite number of points, so you can write down next point would be.
Exactly, yeah. You can't establish what the next point would be because there's always gonna be, you always missed it by infinity. You weren't very close, okay? Make sense? I just thought I'd point that out. I mean, isn't that just, those, grappling with those little conceptual oddities helps you in math. Okay, any other, wanna look at any other of these? Or is that the one that covered most? Okay, good. So, let's move forward then. I wanna just, we kinda talked about this, so. When are we out of here? I gotta gauge. 5 minutes? Oh my gosh. Okay, well, then, I'm not even gonna do this. I can't do it in 5 minutes. Okay, here's what I'm gonna do instead, 5 minutes. I wanna give you something to think about over the weekend, for the last 5 minutes. Okay, here is my philosophical question for you for the weekend. Okay, I would like you to consider whether you believe mathematics is invented or discovered, or AKA uncovered. Is it discovered? Is it already fully in existence and it's discovered? Or is it something that is developed or invented by the human mind? Okay? And we have till 12:30? I said, you're right, okay, this is a little deeper level, but yeah. Yeah, this is, yeah.
What? There is no number 4, it doesn't exist. How do you know? There is no number 4. Like, you can't, you have to have a number 4.
Yeah, you do today. Yeah.